The next electrophilic aromatic substitution reaction we're going to discuss is called the Friedelcrafts alkylation. This is when benzene reacts with an alkyl halide in the presence of aluminum chloride. And the result is, as the name implies, alkylation. You're adding an alkyl group onto the ring. You, you also get HCl as a byproduct. And this reaction is analogous to halogenation, which we just saw, right? Because if you think about how is aluminum chloride behaving, well, it's also a metal halide. And so what happens is aluminum chloride reacts with the alkyl halide. Aluminum chloride is a Lewis acid, and so the alkyl halide is a Lewis base. Lewis acids accept electrons, Lewis bases donate electrons, so we have a donation of electrons from the chlorine, pair of electrons on the chlorine, to the aluminum metal. And again, we get that Lewis acid-base complex conjugate, where now chlorine has a positive charge, the aluminum metal has a negative charge associated with it. And this Lewis acid-base complex conjugate can actually dissociate, right, where the RCl bond dissociates and goes to the chlorine, and you get R+. So you're generating carbocation plus aluminum tetrachloride anion. Now this only happens if R is a secondary or tertiary in nature, right? So if I start with the secondary or tertiary alkyl halide, I can dissociate and I can generate carbocations. If it's a primary alkyl halide, that's definitely not going to happen. And so, I have to think about what type of alkyl halide I have in terms of thinking about the entire mechanism. All right, so now I know that I either have a carbocation present if the alkyl halide I started with was secondary or tertiary, or I have still the complex conjugate if the alkyl halide was a primary alkyl halide to begin with. And of course, I have created these very strong electrophiles. So benzene can behave as a nucleophile, and it can either attack the carbocation, or in the case of the complex conjugate, it can attack the R group, and that RCl bond breaks, right? And of course, the net result is I'm still generating that aluminum tetrachloride anion. And of course, I also get my cyclohexadienyl carbocation with the R group attached, right? Notice again, I want you to focus on that carbocation being stabilized through resonance. So be able to draw those resonance structures. And I'm just giving a little, shortcut here to denote that those other two carbons have a partial positive charge associated with them. So now I have the aluminum tetrachloride anion. It dissociates to provide chloride ions, and now that chloride can be used to deprotonate a hydrogen. Again, those electrons go back into the ring, and we regenerate our aromatic ring, so the benzene ring, and R is substituted. I also get HCl, I also get aluminum chloride. So again, very analogous to halogenation. If you see the similarities, then you're not simply memorizing, each particular mechanism, but you see how they all fit together. Now, for many alkyl halides, when Friedelcrafts alkylations are attempted, you often get rearrangement. And an example of this is if I take benzene and I react it with 1-chloropropane, again using aluminum chloride as a catalyst at 5 degrees, I would expect to see propyl benzene, right? So, typical substitution reaction. When I do this, the yield of this product formation is actually only 45%. and I get another product, and that other product is isopropyl benzene. So I get propylbenzene in 45%, but I get isopropylbenzene in a whopping 55% yield. How is this happening? Obviously, a rearrangement occurred. And if I think about the mechanism of this reaction, here I have my propyl chloride, or 1-chloropropane, reacting with aluminum chloride, forming an acid-base complex conjugate, right? So the chloride donates a pair of electrons to the aluminum chloride, and I get my complex conjugate. So I'm not going to form a carbocation, obviously, but if I think about it, I have a secondary carbon that's attached to that primary carbon, and if I donate a pair of electrons from one of those carbon-hydrogen bonds, and I kick off that chlorine, it in essence is a hydride shift. So I'm getting rearrangement, and I can get hydride shifts, and I can get alkyl shifts. So I have to be very careful. As you know, when there is the potential for carbocation formation to occur, you oftentimes have rearrangements. So the result is I get now a secondary carbocation, the isopropyl carbocation. And it's this secondary carbocation that is going to be favored and give me the greater yield. So benzene actually reacts with this carbocation, right? Again, the pair of electrons from benzene attacks the carbocation. I generate my cyclohexadienyl carbocation with an isopropyl group now attached to the ring. And of course, the aluminum tetrachloride anion can dissociate and remove the proton, regenerating the benzene ring. The result is isopropyl benzene plus HCl plus aluminum chloride. So this is something that we have to be very careful about. Whenever we have alkyl halides and especially primary alkyl halides that have 3 carbons or more, the main product is going to be the result of rearrangement. And so this makes it very difficult to actually put a primary alkyl group onto the ring, right? Other than a methyl group or an ethyl group. Methyl chloride and ethyl chloride can't undergo rearrangement, and so those are very easy reactions to do in terms of Friedelcrafts alkylations. But anything large with a longer chain, propyl chloride, butyl chloride, and so on and so forth, are going to give you rearranged products. Now, we can also use other methods that generate carbocations. And so, if you think about this reaction, the electrophile is a carbocation. And we know of other ways that we can produce carbocation intermediates. One of those ways is if I take benzene and I react it with an alkene in the presence of sulfuric acid. I have seen, we have seen that alkenes will react with sulfuric acid or acids and generate the most stable carbocation. So if I take benzene and I react it with 2-methyl-2-butene in the presence of sulfuric acid, I get this structure, right? And I'd probably name this 2-methyl-2-phenylbutane. It's much easier to name that benzene ring as a substituent, right? Instead of, I guess I could name this 1,1-dimethylpropyl benzene. Either way, it certainly works. Now, how did this happen? Well, I generated that carbocation, benzene attacked the carbocation, and it resulted in that product formation. Now, a similar reaction to Friedelcrafts alkylation is called Friedelcrafts acylation. Here I'm taking benzene and reacting it with an acyl chloride in the presence of aluminum chloride. So again, parallels between alkylation and acylation. And the net result is I get ketones. So this is a way of making ketones. Again, thinking about synthetic strategies, now I know how to make ketones, um, aromatic ketones from benzene and acyl chlorides. And you may not be very familiar with acyl chlorides. They're called acyl or chlorides, or sometimes acid chlorides. Acid chlorides because they're actually derived from carboxylic acids. So I'll use these terms kind of interchangeably. I tend to use acyl chloride, that term, more than acid chloride. Um, but understand that it means the same thing. And as a matter of fact, to make acyl chlorides, you start with a carboxylic acid, right? You treat that carboxylic acid with SOCl2 and it produces the acyl chloride. SOCl2 is called thionyl chloride. So reaction of a carboxylic acid with thionyl chloride produces an acyl chloride. This is typically how we actually get acyl chlorides. We generate them in the lab in situ because they are fairly reactive, and they actually will react with water, even water in the air, and they will be converted back to carboxylic acids. So when you if you bought a bottle of a particular acyl chloride, oftentimes if it sits for a period of time, it actually goes and forms a carboxylic acid by reacting with water. And so to eliminate that, we typically just take a carboxylic acid, treat it with thionyl chloride to know that we're getting the acyl chloride present. All right, so in terms of the mechanism of this reaction, again, let's think about parallels with alkylation versus acylation. What's my electrophile? Well, why is the aluminum chloride present? It's there to act as a Lewis acid, right? And the acyl chloride is a Lewis base. So I donate a pair of electrons from the chlorine to the aluminum, and I generate my acid-base complex conjugate. Now this time around, I can actually dissociate that carbon-chlorine bond, and I generate this species right here. So R, C, double bond O, and now that carbon is a carbocation. Now the unique thing about this type of carbocation is that it has a resonance stabilization, where I can take a pair of electrons from oxygen and donate them to form a carbon-oxygen triple bond. And these resonance forms are of what's called the acylium ion, Now I have the acylium ion, and notice it's electron deficient, right? The oxygen is bearing that positive charge. And as a matter of fact, if we look at those two resonance structures, we see that the resonance structure on the right is actually the major resonance contributor. Why? Because all of the atoms have an octet of electrons around it. So even though that oxygen has a positive charge, this particular structure is more stable. However, when benzene reacts with the acylium ion, it always attacks the carbon. It does not attack the oxygen. And so we get nucleophilic attack of the acylium ion on the carbon. We get carbon-oxygen triple bond. One of the pi electrons goes up to the oxygen to essentially neutralize it, right, so that it has no net formal charge. And now we generate our cyclohexadienyl carbocation with a C double bond O R group coming off. So here's my ketone. And again, thinking about resonance, you should be able to draw the resonance structures of all of these intermediates. So we also have the aluminum tetrachloride anion, very similar, right, to that of alkylation and halogenation as well. The aluminum chlorine bond dissociates, generating chloride ions that can then deprotonate that hydrogen, and the electrons go back in to form the ring, and so we get our curved arrows that look like this. And our product is now a ketone, right? Now, the cool thing about Friedelcrafts acylation and the big difference between it and alkylation is there are no possible rearrangements. The acylium ion is stabilized and therefore you don't get possible rearrangements. So let's look at a couple of examples. If I take benzene and react it with this is acetyl chloride. It's a derivative of acetic acid, right? CH3C double bond OH. So acetic acid treating that with thionyl chloride gives you acetyl chloride in the presence of aluminum chloride, and I get this, right? This is called acetophenone. Acetophenone. Again, it's a ketone. Now I can also treat here I have benzene, and it's being treated with butanoyl chloride. So there's a 4-carbon chain that we're essentially placing on the ring. Notice for alkylation and acylation, we're creating a carbon-carbon bond. So when we're thinking about syntheses, that's something we always want to be thinking about. How do I create, what reactions form carbon-carbon bonds? Alkylation does, acylation does as well. The product of this reaction is this. And so this would be called phenylpropyl ketone. Phenylpropyl ketone. Now, if I think about this particular structure, notice when we were talking about Friedelcrafts alkylations, we said that it's very difficult to put a primary alkyl group on the ring because you get rearrangements with primary alkyl halides. And so if I envision being able to take this, which I know I'm not going to get rearrangements, if I were able to reduce that carbon-oxygen double bond to a methylene group, then I have the potential of being able to put a primary alkyl group onto that benzene ring. Is there a way to do this? Well, I wouldn't be talking about it if there wasn't a way to do this. And as a matter of fact, there's an excellent way of making primary alkyl benzene derivatives. There are 2 methods, right? So the first method of reduction is called a Clemmensen reduction. Clemmensen reduction. And what it does is it takes a ketone, right? So notice I'm not simply limited to phenyl ketones. I could take any ketone and treat this with a zinc mercury amalgam in the presence of hydrochloric acid. So this is run in hydrochloric acid with a zinc mercury amalgam. And the zinc is a very strong reducing agent. The mercury essentially slows the reaction down a little bit because zinc is such a good reducing agent. And the result is that I convert the carbonyl into that methylene group, right? So I get RCH2R primed. I'm converting a ketone into an alkane. Again, thinking about classification of reactions. These methods, Clemmensen reduction and the next one, are converting a ketone into an alkane. Now, one thing to note about this particular method of reduction is that we're in very acidic conditions. So sometimes we have to think about other functional groups and the effect of acid that acids may have on those functional groups. And if we have functional groups that may be prone to protonation, we can use a different reduction method called the Wolff-Kishner reduction. And the Wolff-Kishner reduction takes, again, a ketone, treats it with hydrazine. So H2NNH2 is called hydrazine. In the presence of a base like potassium hydroxide or sodium hydroxide, and a solvent that has a very high boiling point, right? So this is diethylene glycol. And the reason for this is because we have to heat this reaction up a lot, right? Notice the temperature is at 200 degrees Celsius. Again, the product is the reduction of the carbonyl all the way down to a methylene group. So again, we're taking a ketone and we're converting it into an alkane. This is in basic conditions. So you have two methods that you can use, two different types of reagents that you can use that will give you essentially the same thing. And so sometimes you might want to use acidic conditions and sometimes you might want to use basic conditions. Now the whole idea behind this then is that now I can take benzene and in the first step I can react it with an acyl chloride, and in the second step that ketone that's formed from the Friedelcrafts acylation can then be reduced. So I'm adding 4 carbons onto the benzene ring, and that benzylic carbon is a ketone, and I'm going to reduce that ketone to a methylene group, and the result is I get butyl benzene. I'm now able to synthesize a primary alkyl benzene derivative.